Good evening. We are Group 17, and today we'll be presenting our work on the Kaggle competition for plant seedlings classification. I am Majid, and later I will be joined by Jason, Yong Xian, and Wayne. Let's move on to the problem statement. In this Kaggle competition, the task is to identify the differences between a weed and a crop seedling. We are given an RGB image of the plant, and we need to predict the species of the plant. The motivation behind this competition is to achieve better crop yields and better stewardship of the environment using the power of computer vision. The evaluation metric that will be used is the F1 score, whose equation you can see on the slide. Let's move on to the exploratory data analysis. The goal of the exploratory data analysis is to gather as much information as possible from the dataset to choose the right approach to tackle the statement of problem. This particular dataset provided by the competition contains images of 960 unique plants belonging to 12 species at various growth stages. In the training set, there are 4,750 labeled RGB images of plant seedlings classified into 12 different species. In the test set, there are 794 unlabeled images of plant seedlings. This gives us a trained test split of about 85 to 15. The sizes of the images in the dataset are not standardized, with sizes ranging from 1285 pixels to 154 by 154 pixels. As for the data distribution, the images are non-uniformly distributed in the training set. Classes like maize have half the number of images as compared to classes like loose silky bent. These variations in the training data could possibly introduce bias into our trained model's predictions, wherein the model is more likely to predict loose silky bent because of the greater number of instances in its training phase. Using RGB channel analysis, we found that the green channel contains the most encoded relevant information for this project, and using BGR histograms, we found interesting differences in the color and tonal variations among the different classes. To gain an even deeper level of understanding of the dataset, our team decided to use principal component analysis, which is a technique for reducing the dimensionality of this dataset, increasing the interpretability, but at the same time minimizing information loss. This is done by creating new variables that are uncorrelated to represent multiple features in the image data. From the graph on the slide, it can be noted that all classes are generally grouped together, aside from a few anomalies. This means that there is very little segregation in the principal components for different classes, which makes the problem statement more difficult to tackle. Further, we have identified two pairs of classes, the first pair being black grass and loose silky bent, and the second pair being scentless mayweed and cleavers. Since they are almost similar visually, the features trained will have very closely packed data points, which may require the model to be a little more flexible in order to properly identify and classify such classes. As for the challenges in tackling this problem, the size of the dataset is relatively small with only 4,750 images, considering the dataset represents 12 different classes. This makes deep learning models prone to overfitting. Secondly, our principal component analysis showed that the segregation in features between different classes is very small, which makes it difficult to use traditional clustering to separate the classes. Thirdly, the level of accuracy that was obtained when training the Inception ResNet v2 model, as Yong Xian will discuss later, did not always carry over to the test set. Hence, several penalization and regularization techniques, which will be discussed later, had to be employed to get a more consistent result across the two sets of data. Next, moving on to the pre-processing, our team used three basic techniques, namely image augmentation, resizing and flattening, and image normalization. Furthermore, to improve the performance of our models, we use pre-processing techniques such as color-based segmentation to remove additional noise in the training images. Another technique we used is regularization, which is a form of regression that constrains or shrinks the coefficient estimates towards zero. One of the regularization techniques we applied is dropout. This technique prevents complex co-adaptations on the training data by randomly selecting neurons of a neural network to be ignored. We also experimented with an augmentation technique called contrast-limited adaptive histogram equalization. It is mainly used on medical data to highlight the image's contrast for better visualization, as shown in the image on the slide. However, due to time constraint, we could not further our experimentation, and the initial result of incorporating this technique was not as good. Lastly, we used gradient accumulation to allow us to increase the batch size while using our personal GPU that is limited by its memory. Gradient accumulation multiplies the batch size by updating its weights once every stated number of batch size on the trade-off of increasing runtime. Now let's move on to the actual approaches that we use to solve this problem. Firstly, we use k-means clustering to quickly set a benchmark before experimentation with other methods. K-means clustering is an unsupervised learning method which requires a deterministic number of classes, which in this case is 12. Subsequently, 12 random points are chosen from the dataset to act as the centroid for each cluster. However, being an unsupervised learning algorithm, and given that there is a heavy overlap between the clusters as seen by our PCA analysis earlier, the accuracy of this approach was a meager 29%. Next, to better success, we used k-nearest neighbors, which is a supervised learning algorithm that performs regression and classification. This lazy learning algorithm works by finding distances between a queried data point from that of the other data points. It classifies the image then based on k number of examples that are closest to it. The k value that we chose is 5. The F-score that we got from Kaggle in using this algorithm is 53%. We then moved on to using support vector machine, which works by finding a hyperplane in an n-dimensional space. The data points are plotted in an n-dimensional space according to the value of the n features. The hyperplane is computed such that the data points of different classes are effectively segregated. Of the primitive machine learning methods, this algorithm showed us better success with a Kaggle F-score of 63.97%. Now I'll pass the time on to Jason, who will be talking about GoogleNet.
Now we are moving on to a more well-known model for image preprocessing, namely GoogleNet. GoogleNet is the first inception network model developed by Google. It contains a total of 27 layers as shown in the figure. So the intention of GoogleNet is to expand the depth and width of the network by stacking deeper convolution layers together. The figure in the left shows the knife inception model that performs convolution on input with different sizes of filters and a max pooling layer, which are then concatenated and sent to the next inception model. However, the issue with this deep network is the expensive computation that is needed. To solve this, GoogleNet introduced an inception model with dimension reduction as shown in the figure on the right. It introduced a 1x1 convolution to both 3x3 and 5x5 architecture to reduce the dimension, which eventually reduces the computational cost. However, adding this layer creates another problem called representation bottleneck, which highlights the loss of information if we reduce too many dimensions. Fortunately, this problem has already been addressed in the later version of Inception Network. So, for this project, our team used the model imported from Torch Vision. There are some pre-processing such as random horizontal and vertical flip, as well as some resizing. So the parameters used are shown in the slides. This model performs quite well and manages to achieve an F1 score of 84.256%. Moving on to the next approach, namely VGG16, which is a variant of VGG model. It consists of 16 convolution layers and 3 fully connected layers as illustrated in the figure. So VGG16 contains different layers such as convolutional, pooling, fully connected, and softmax layers. Most of the convolutional layers are followed by max pooling layers, which is responsible for narrowing the layers down. So the max pooling utilizes a 2x2 pixel window with write 2. In the end, VGG16 has 3 fully connected layers, the first two with 4096 nodes and the third one with 1000 nodes, followed by a softmax layer to provide the output. So the basic idea of VGG16 is to increase the number of hidden layers within the architecture. As mentioned before, the problem with deep architecture is expensive computations and memory. However, as seen in the table, which is taken from a study by Simonian, the number of parameters of VGG16 is not that much greater compared to the rest of the architecture. So this is achieved because VGG16 uses small 3x3 filter sizes instead of a normal 5x5 or 7x7 filter. So for this project, our team used the built-in VGG model from Keras. We are using similar pre-processing as the previous model GoogleNet, and the parameters used are shown in the slides. This model actually performs really good and manages to achieve an F1 score of 96.92%.
In the Inception ResNet version 2, it is a combination of InceptionNet and ResidualNet. The figure on the right shows the architecture overall, where there are 3 inception blocks and 2 reduction blocks. There is a total of 446 layers and one of the top models in Kira's pre-trained model. The following 3 inception blocks, A, B, C, are professionally engineered to increase the width of the network by multiplying n times n convolutional blocks. Research has been done to reduce the computational cost by using multiple smaller size convolution to replace the expensive large convolution of 5x5 and 7x7, which is proven to be very effective. The motivation of Inception ResNet is to increase the network layers by increasing the width instead of just the number of layers, the depth. This will in turn cause issue as well. Therefore, to overcome the overfitting, vanishing gradient, and computational issues, skip connection from residual net is introduced to allow networks to traverse in case the layer do not provide substantial increase in the performance. An interesting note that the author, since the first version of InceptionNet, has intuitively used 1x1 convolution to reduce the dimension of the network, at the same time factorizing the convolution. This has evolved over time to include asymmetric convolution of 1 times n as shown in the inception block. We applied this model with Keras pre-trained on ImageNet dataset. We have adjusted the pre-processing and augmentation to fit the model. We optimized with Adam using 5e-5 learning rate and batch size of 10 with gradient accumulation on 100 epochs. To counter the overfitting issue with high epochs, we added an additional dropout layer, and as the training dataset are already very low, we implemented only 5% of validation set to ensure that our model can properly train the features. We have even tried eliminating validation set to only train and test. This has proven to improve the results slightly. This model is currently our best performing of 98.74% in Kaggle. One of the important findings we had when training our model with this dataset is that feature-wise standardization and normalization as well as zero-component analysis whitening do not work well with this dataset, as some of the images in the dataset has very little important features as shown in Claire's example. So with feature-wise standardization and Zika whitening, it removes too many important features that our model is not able to train them. Therefore, it lowers the accuracy of the results overall. We also find that normalization do not work well with gradient accumulation because batch norm statistics cannot be accumulated.
Our group performed several novel approaches to improve the overall performance. First, in terms of exploratory data analysis, our team used principal component analysis and BGR histograms to give better understanding on the nature of the dataset. This allowed us to do color-based segmentation to remove unnecessary features before carrying out the training process. We also did some image augmentation during pre-processing, which improves the performance significantly. In terms of the model training itself, our team used gradient accumulation, which allowed us to train the model with higher batch size with a smaller GPU capability. We also included dropout layer in our model to prevent overfitting situations for a model with high number of epochs. Throughout the project, there were many lessons learned related to both technical and non-technical skills. We learned about the characteristics, pros and cons of various new models, which help us find the suitable model for a specific problem. We also learned how to tune up different sets of parameters to find the best model. Aside from technical knowledge, during the project, we also learned how to manage time properly and communicate well with other team members in order to achieve the goal. This project helped us to experience the entire machine learning process. First, exploratory data analysis allows us to understand the context and characteristics of the dataset. Next, pre-processing is important because it helps us to improve the performance significantly if it is done properly. And lastly, we proceeded to build a model. For this project, we implemented various models ranging from traditional methods such as K-means, KNN, and SVM to newer methods such as GoogleNet, VGG16, and Inception ResNet. Our team managed to build a model using Inception ResNet, achieving the highest accuracy of 98.74%. That is all for our presentation. Thank you.